let me feel your mind for 40 minutes. So this kind of transitions back to 6.3 in your book. Okay, 6.2 is just about the unit circle, which we covered everything you need to know. Fundamental identities is a different topic. It's related to the unit circle, and a lot of the identities come from the unit circle, but it's a slightly different topic. You guys understand what the word fundamental means, right? What's fundamental mean? Basic, necessary, foundation. I cannot understate this. If you do not have your fundamental identities memorized and internalized and part of your DNA, you will flounder and you will get points off on this test and on the next test and in life. Okay, these are irreplaceable. Okay, you need to know them. If you doubt me, you can try not to memorize them and not to understand them. And if you figure out how to get through this class with that, let me know. Now, there are basically three types of fundamental identities. Reciprocal identities, quotient identities, and Pythagorean identities. The reciprocal identities and the quotient identities we've kind of already talked about, but let me state them here for you anyway and show you quickly where they come from. Remember, we have these definitions now. We have a bunch of definitions, but the most recent one. If I ask you what sine of theta equals or what cosine of theta is, you can just refer to your unit circle definition. Sine of theta is y, cosine of theta is x. Tangent of theta is y over x. And then you have all your reciprocal functions, cosecant theta, secant theta. 1 over y, 1 over x, 1 over, oh, I'm sorry, x over y. So what your fundamental identities do is they take these definitions and try to express all the relationships. So for example, because cosecant of theta is 1 over y, you can replace y with sine theta. So saying that cosecant theta is 1 over y is the same thing as saying that cosecant theta is 1 over sine theta. So if you look over here in the second box on the right, it says cosecant theta is 1 over sine theta. So for each one of these functions, you have a reciprocal identity. Cosecant theta is 1 over y or 1 over sine. What about sine theta? Sine theta is the reciprocal of cosecant. So it goes this way. Cosine theta and secant theta, how are they related? They're reciprocals of each other. So for secant theta, you can write 1 over cos theta. And for cos theta, you can write 1 over secant theta. Same thing for tangent and cosine. Tangents, 1 over cotangent theta, because they're reciprocals, and cotangents 1 over tangent. So these are called the reciprocal identities. And it's really just looking at these definitions and doing a little bit of substitution. Instead of y, call this sine. The next set are the quotient identities. These have to do with tangent and cotangent. And again, they come right from the definition. Tangent of theta in this definition is y over x, opposite over adjacent. But I know y is sine and I know x is cosine. So instead of y over x, I can write sine over cosine. Same thing for cotangent x over y. I can write cosine over sine. The last set, and we'll do some examples, we'll use all these in a second. The last set of identities are the Pythagorean identities. And they're like the Pythagorean theorem. They're just ever present. We need them all the time. These are the three Pythagorean identities. Let me show you where they come from quickly. First one is the easiest to understand. The first one says that sine squared of theta plus cosine squared of theta equals 1. Do you know why this is true? No, sine and cosine are in no way inverses. They're co-functions, but that doesn't come into play here. Sine on your unit circle, what's sine equal to?
Y.
Sine of theta is equal to the y value, right? And what's cosine equal to? X. And what is the equation that every point on the unit circle satisfies? X squared plus y squared equals 1. That's how you belong to this circle. That's like the criteria to get into the club. You have to meet x squared plus y squared equals 1. But x is cosine and y is sine, so cosine squared plus sine squared equals 1.
It's like the original equation. You'll notice in this equation, or in this identity, so the difference between an identity and an equation, in case that's not clear, is that identities are true for all possible values of the variable. All right, if I write an equation on the board like, if I write something on the board like x plus 5 equals 7, this is only true for one specific value of x. This is an equation. But if I write an identity, this is true for all theta. So whether I put pi over 4 and pi over 4, or pi over 2 and pi over 2, or 30 degrees and 30 degrees, this is always true. They have to match. The angles have to be the same. But as long as they're the same and you're doing sine squared plus cos squared, you're good.
Can you explain why it's 1 again? Because it has to follow that, right?
Well, I mean, another way to do it is like this. The distance on this is 1, right? This is x, this is y. So I know from the Pythagorean theorem x squared plus y squared equals 1. But I also know from the fact that cosine is adjacent over hypotenuse that this is the same thing as cos theta. And I know that since sine is opposite over hypotenuse, this is the same thing as sine theta. So it's called the Pythagorean identity because it's related to the Pythagorean theorem. If that makes more sense.
Yeah, I just imagine you replacing sine with x now and it's squared. Okay.
So there's these other incarnations, these other mutations, I guess, of the Pythagorean identity. And they do come up, and you should either memorize, actually you shouldn't. You should be able to
derive them pretty quickly. So what I usually do, I know this guy. This guy is memorized because, I don't know, I've just been looking at it for so long. It's pretty straightforward. Sine squared plus cosine squared is 1. But what I can do to get my other Pythagorean identities is either divide by sine squared or divide by cosine squared. So what I mean is, if I take everything in this equation and divide by sine squared theta, or if I start from the beginning and divide everything by cosine squared theta, I will get those other two forms I have written up there. So ignore the squareds for a second. What's sine over sine? 1. Or sine squared over sine squared, it's still 1. So this tells me that 1 plus, what's cosine over sine? Right up there in the box, right? Cosine over sine is cotangent, according to my quotient identity. Because it's squared, you'll have cotangent squared. Reciprocal identities, what's 1 over sine? Cosecant. So 1 over sine squared becomes cosecant squared. This is your other Pythagorean identity. Take this master identity here and instead divide everything by cos squared. Sine squared over cos squared. Well, forget about the squared. Sine over cosine. What's that?
Tangent.
That one's tangent. Sine over cosine is tangent. So this guy here is tangent squared. Cosine over cosine. 1. Reciprocal, 1 over cosine.
Secant.
The reciprocal of cosine is secant, so this will be secant. The first hurdle in this portion of the class is honestly memorizing all of these. There are techniques you can look on YouTube or somewhere, search it. Some people, there's this hexagon that you can remember that helps you get all the fundamental identities down. I don't have anything good. I've never found anything better than just using them again and again until I happen to that. Right. But there are some, ask a tutor, ask Google. I'm sure you'll find some mnemonic devices. But you have to have all three of these identities, these categories of identity down.
Pythagorean.
The last three are called the Pythagorean identities. Yes.
Can you get these exact notes on your website? Can you show everybody just so I know?
It's right underneath the study. Did you get to the review sheet?
I got to the review sheet, so it's right
It's
there.
right underneath there.
Okay.
So the review sheet's right here.
Um,
If you go down, it has the notes.
oh,
And this one is, sorry, this one is the unit circle in front of it.
okay.
So there's a couple more properties. I'll talk about them for a second here. Let me start with the bottom because we already did these. These are the co-function identities. You remember these? Right? If you want to talk about sine versus cosine, right? They're co-functions. Sine and cosine are co-functions, and if you want them to be equal, the angles have to add up to 90. The angles have to be complements. Right? So sine of 30 is equal to cosine of 60. Secant of 25 is equal to cosine of, or cosecant of 65. So we touched on those a little bit before, so I'm going to read over them now. Let me go up from there. What do you think these periodic properties mean? Now these are properties. These are not fundamental identities. So what I mean is, you will hurt if you do not know these properties, but you will not die. Okay, they're not fundamental. Right? It's good for you to memorize them. It'll cost you points if you don't, but they're not as crucial as the first set. But anyway, what do you think this periodic property means? Sine of theta plus 2n pi equals sine of theta.
That any number of revolutions is the same sign.
Yes, revolutions do not affect sine. So the periodic property is the first one. Say that sine of theta plus 2n pi is equal to sine of theta. So the way you should read this, the way you should interpret this, is if you take sine of an angle theta, but add any number of full revolutions, right? Because 2 pi is a revolution. And the n lets you add any number of revolutions. So if n is 1, 1 revolution. If n is 2, 2 revolutions. If n is 5, 5 revolutions. So whether you do sine of theta plus, let's just take n equal to 1. Whether you do sine of theta plus 2 pi or sine of theta, it's the same thing. So here's a little diagram. Here's my unit circle. Here's theta. What do you think theta plus 2n pi, how can I represent that schematically on this diagram? Theta plus 2n pi means go any number of revolutions and then back to theta. So this would be an example of theta plus 2n pi. But you land in the same place. So your y value on the unit circle is going to be exactly the same. So sine of, whether I go theta or I go theta plus 2n pi, I will get the same sign. That's what this is. Same S-I-N-E, sine. The same is true for cosine. Because whether I go theta or I go theta plus 2n pi, I get the same x value. Why do you suppose tangent, if you look at tangent, it only has n pi? What's that mean? Yeah, so tangent will repeat after going 180 degrees. Oops. So tangent of theta plus n pi is equal to tangent of theta. So schematically what's going on here, whether you go theta right here, say, or you go theta and then a half revolution, right, because pi is only a half revolution, you're going to get the same tangent value. Over here, the point on your unit circle would be xy. After going theta plus n pi, say just 1 pi, theta plus 1 pi, what would this point be over here? Yes, it's diametrically opposite. It's across the origin. So what's going to happen is it's just going to pick up a negative sign on the x and a negative sign on the y. But tangent is the same because tangent is y over x. So whether you divide these two numbers, you divide these two numbers, you get the same thing because the negatives cancel. That doesn't happen with sine or cosine, right? If you end up way over here with sine, that's a different y value. Right? So these are different y values. So sine, you cannot go a half revolution and expect to repeat. Right? Sine, you have to go a full revolution. That's why this is 2 pi here. Tangent, though, if you go a half revolution, the sines will be the same, so the tangent will be the same. Yes?
Does that mean cotangent is the same?
Yes.
Like 180 degrees again?
Yes. Yes, because cotangent is x over y, or the reciprocal of tangent, it has the same property.
And then negatives cancel.
Yes, because the negatives cancel. So cotangent satisfies this. Theta plus n pi will be cotangent of theta. Do you guys know what even and odd functions are? Remember? Function is even if it satisfies a certain property, and a function is odd if it satisfies a different property. And it has to do with negatives. Right? The way even functions work is if you plug a negative inside, it's as if you hadn't put the negative in at all. Like x squared is even. Whether you square 3 or you square negative 3, you get the same thing. So this is what an even function satisfies. If you put a negative inside, it just vanishes. It's not important. An odd function, if you put a negative inside, the negative pops out front. So we went over this to some extent in 126, we should have. But now we're applying this idea to sine and cosine if you look up at top there. I talk about putting a negative into sine or putting a negative into cosine and seeing what happens. So the kind of the bottom line here is that cosine is even and sine is odd. So when I say cosine is even, what I mean is if you put a negative inside, it vanishes. What I mean by sine is odd, if you put a negative inside, it pops out front. Why do you think that is? What does it mean to put a negative angle in? It's going down first, clockwise. So schematically, here's a theta, here's a negative theta. My point here, say my point here is xy. What would this point down here be? The x will be the same, because it's a reflection. The x will be the same, but the y will be negative. So look at cosine. Whether you go to theta or you go to negative theta, what's your x value? Same thing. So cosine doesn't care whether you put in a negative theta or a theta, it'll give you the same thing. These x values are the same. Sine cares. Sine makes a big deal out of it. If you go from theta to negative theta, the y value flips. Right, opposite sign. So that's why if you put a negative angle into sine, you get the opposite sine answer. SIGN, opposite SIGN. There's a tangent property too. Tangent odd as well. Meaning that tangent of negative theta is equal to negative t. It's the same reason. Right? The sign changes for y over x. So let me look at we're going to do this example. I want to look at some problems that will help you understand these identities and these properties. The first one I gave you here, let sine theta equals 7/8 and suppose that theta is between 0 and 90 degrees. Use identities to find the other 5 trig functions. So what I'm trying to do here when I say use identities to find the other 5 trig functions is I want you to play detective and make use of all of these relationships to go from sine theta to every other trig function. So this is algebraic in nature. I'm going to use a bunch of formulas. You have sine theta, you have to find cos theta, tan theta, secant theta, cosecant theta, cotan. First one I would suggest finding if you have sine, well, you can find them in whatever order you want, but eventually you're going to need cosine, and it's the hardest one, I think. Okay? So I'm going to find cosine theta first. Now I'm only using identities because the instructions said use identities. So what you have to do is you have to scour your identities and find one that relates sine theta to cosine theta. Right? It can't have anything else in it. If it has anything besides sine and cosine, it won't work, because all I know is sine. Right? So as I look at my identities, sine theta equals 1 over cosecant theta. That doesn't help me, it doesn't have cosine in it. Right? Cosine theta equals 1 over secant theta. That doesn't help me, it doesn't have sine in it. Right, so you go through. This one might look promising. Tangent of theta equals sine theta over cos theta. But why is that no good? We don't know tangent. So the only identity actually that has sine theta and cos theta and nothing else is your Pythagorean identity. That's why it's pretty powerful. Pythagorean identity allows you to go from sine to cosine. So I have sine, but I know sine squared theta plus cos squared theta equals 1. Big whoop, how does that help me get cosine theta? You can substitute. Right? Instead of writing sine of theta, I'm going to write 7/8. Because that's what sine of theta equals. So there's a substitution that I can do here where I replace sine of theta with 7/8. What about this square? Keep it, doesn't go anywhere. Square it. Rewrite everything else. I took the 7/8, put it in here, got this. Again, I'm trying to find just coast data. So what can I do with this? Yeah, so I want to isolate coast data. This is like your variable. This is the guy you want to quarantine. I want to isolate this. So the first thing I would probably do is, well, I know what 7/8 squared is. 7/8 squared is 49 over 64. You just multiply 7 times 7, 8 times 8. And then I can subtract this over to the other side. Because again, I want to isolate this quantity. This goes to 0. What's 1 minus 49 over 64? Negative. 15 over, positive 15 over 64, I believe. So we have to get a common denominator here, if nothing else, right? So if you're not sure what's going on here, you think of this as 64 over 64, and subtract 49 over 64, and that gives you 15 over 64. So when you do this subtraction, you get this. Which means I know cos squared theta equals 15 over 6. But I didn't ask you for cos squared theta. I asked you for cos theta. So what do you do? Square root. Square root that bad boy. Now you got to be careful here because when you square root both sides, the square root of cos squared you can put as cosine, but because you square root of both sides, you need a plus or minus. At least for a second. How do I know whether to choose plus or minus here? Quadrant. Cosine is positive or negative in the first quadrant? Positive. Cosine is the x values. Between 0 and 90, all your x values are going to be positive. So you choose this. Where'd that 8 come from? So, this is algebra. This is not trig. The only trig I did here was when I started with this identity, and I said I'm in the first quadrant, so cosine's positive. This part here, oh. Questions about what I did to get cos theta?
So,
Yeah.
how come you have to do like 64 over 64 minus that, so just 1 minus that? Since it be 1 minus 1/4, how do I remember to do that?
How do you remember to subtract fractions?
I mean, just because it looks like 1 minus 49 over 64.
It is. That's what it is.
But I get 1/4 in my calculator.
Then you're doing 1 minus 49 over 64 incorrectly. This is this. And in order to do that, you have to get a common denominator. And if the calculator is telling you anything other than 15 over 64, it's something's off. But we can look at that. How do we finish this up? How do we get the rest? How do we get tan theta and then the reciprocals? Tangent theta is Sine over cosine. Quotient identity. So now I have another piece of the puzzle. I have cosine. I have sine. So tangent is sine over cosine, which is 7/8 over root 15 over 8. Flip and multiply. Eights cancel. 7 over root 15. Which you can rationalize. 7 root 15. Yes, sir.
In that first part, could
Yes,
you
sir.
just think of it as y over r, and then y would be 7, r would be 8, and then you could just draw a right triangle, and then, no?
Yes, but the instructions that use identities.
Oh,
So the point, and as is the point in a lot of math class, a lot of math problems, the point is not so much to get to the answer, but the point is to show you a specific, method so that you understand identities more. So the point of this problem is that you understand identities. If I don't say use identities, you can do whatever you want, and that will work. That is a valid method. That's what we did in 6.3. But I purposely want to use identities so you can see how these work. You guys know how to get the last three? Yeah, cotangent theta is 1 over tan theta. So flip tangent theta. Secant theta is 1 over cos theta. So flip cosine. And cosecant theta is 1 over sine theta. So flip sine. You don't have to make a big deal out of it at this point, okay? Cotangent is the reciprocal of tangent. So if you write this, then you can just flip it and say, okay, I took tangent and I flipped it. That's cotangent. Secant is the reciprocal of cosine. Take cosine and flip it. Which if you rationalize. Sine. So cosecant is 8/7. All right, let me show you one more thing. Let me show you one more thing. And then I'll let you. I said I wanted to do this last example, and I do, but I can't. So, what I want to show you instead is something on the review sheet. Way down here, 14. 14 and 15, really, but mainly 14. This is going to hurt you. Okay? This is using identities to simplify things. So what you're supposed to do on these problems is take these identities we spent the last 40 minutes trying to understand and apply them in any way that you possibly can to simplify the expression. So take, for example, part A. A simple one. I gave you the expression secant of 8 radians times cotangent of 8 radians times sine of 8 radians. And I want you to use identities to actually simplify this. How do you think you can do that? What do you think that means? Try to put them all in terms of the same functions. So for example, secant is 1 over what? 1 over x, or in terms of identities, secant is 1 over cosine. Cotangent is cosine over sine. Sine is just sine. You don't need to simplify it because you already have a sine 8 in the denominator. So you see what happens when you multiply all these? So what I did is I went back in my head, I looked at my identities, right here. Actually, I only use these two. And I said, okay, what can I replace secant with to somehow simplify this? 1 over cosine. What can I replace tangent with? Cosine over sine. Don't replace sine, then things cancel.